So in beginning calculus classes, you always work over the real numbers, but you're never really told why the real numbers are so important. They're just some kind of plug for holes that happen in the rational numbers like pi and the square root of 2 and so on and so forth. But I was thinking, is it possible to do the normal stuff from like a calculus 1 class without the real numbers at all? In other words, can we define calculus on functions that have a domain of the rational numbers and a codomain of the rational numbers? And I want to approach this a couple of different ways. First, I want to look at, does continuity make sense on the rational numbers? And then can we maybe restrict the type of functions we're working with so that continuity does make sense if it doesn't already? And then after that, maybe we'll look at some derivatives. Can we take derivatives over functions of the rational numbers? And then finally, what about the classic theorems from Calculus 1? Are they still true over the rational numbers? Okay, so let's get into it. So let's recall that a function is said to be continuous at a point A if the limit as x approaches a of f of x equals f of a. So, there's also this epsilon delta definition of the limit, but we're going to go ahead and use this kind of simplified definition of the limit since we're approaching this at the level of like a calculus 1 class. So I want to open up with a troubling example. In other words, some example where continuity does something weird if we're only considering functions on the rational numbers. And the example I want to look at is the following. So let's take this function from q to q, and we're going to define it in the following way. So you can get really fancy with this, but we're not going to get that fancy. We're just going to define this thing as follows. So it's going to be f of x, and it'll be given by 1 if x is less than the square root of 2, and it'll be given by 0 if x is bigger than the square root of 2. And you might be troubled here because I'm using the square root of 2, which is known to be an irrational number, but notice I haven't said what to do if you plug in the square root of 2 because the function is not defined there. It's only defined for an input of rational numbers. And furthermore, since it's only taking on the values of 0 and 1, it only has outputs of rational numbers as well. So let's go ahead and look at a graph of this function. So it's a pretty easy step function. So if we go over here to the square root of 2, which I can put there on the real number line, although since we're considering these as rational axes, this actually occurs as a whole on this rational axis. And then this function is doing kind of the following thing. So it is 1 up until we get to the square root of 2, and it is 0 after the square root of 2. And notice I've made this really fine dotted line instead of a solid line because we're over the rational numbers here. And the rational numbers have these infinitely many holes everywhere, just like this hole at the square root of 2. Okay, great. Now what I want to look at is the continuity of this thing. So if we were over the real numbers, we would say that this thing is continuous everywhere except the square root of 2. But the square root of 2 is not even in the domain of this thing. Notice the square root of 2 is not in the rational numbers, so we don't have to consider it at all. So let's maybe just notice this. For all a in the rational numbers, we have the limit as x approaches a of f of x equals f of a. Great. And so we can really see that because this boils down to two cases. One is if a is less than the square root of 2. Great. But that means we have the limit as x approaches a of, well, f of x, if x is less than the square root of 2, is equal to 1, and that's equal to 1, which is f of a. And you might be troubled here, but let's recall that if we're at a point A, let's put it here, it's less than the square root of 2. Regardless of how close it gets to the square root of 2, we can always find a little interval made up of rational numbers around it to take a two-sided limit. So in fact, this thing is continuous for all elements of its domain, which, like I said, is a little bit troubling because this is clearly some sort of step function which should not be considered as continuous. Okay, well, so maybe we should limit ourselves to functions that are not piecewise defined to some kind of nicer functions so that we don't have to worry about strange things like this. So let's just go ahead and say we limit ourselves to rational functions. In other words, quotients of polynomials. Notice that exponential functions would also cause some trouble because at most inputs in the rational numbers, you would get outputs outside of the rational numbers. So I'll let you guys think about that more deeply, but from here on, we're only going to consider rational functions on the rational numbers. And let's see what could maybe go wrong with that. So I'll clean up the board and then we'll do that. So in the last board, we saw something troubling happen when we looked at piecewise type functions defined over the rational numbers. They ended up being continuous when really they shouldn't have been continuous. So we said, well, maybe we'll just consider rational functions, in other words, ratios of polynomials, as the only functions that we can work with in our calculus from Q to Q. So now let's go ahead and look at the derivative. So I want to recall real quick that the derivative in real variable calculus is defined in the following way. So we generally say f prime of x, and that's the limit as h goes to 0 of f of x plus h minus f of x over h. Now, we could make this a definition over rational valued functions just by saying that this limit is also occurring as h is only from the rational numbers, but we can actually be a little bit more heavy-handed than that in order to really show that we're only over the rational numbers, and we can do that in the following way. Let's make our new definition of our rational derivative in the following way. We'll say f prime of x equals the limit, and then instead of having h go to 0, we'll have n be a natural number and n go to infinity. And we're essentially making the change of variables h equals 1 over n. So notice if n goes to infinity with that substitution, h will go to 0. So we'll have f of x plus 1 over n minus f of x over 1 over n. Great. So now we can simplify that a little bit maybe if we wanted to. So that's the limit as n goes to infinity of n times f of x plus 1 over n minus f of x. Great. So that's our new rational valued derivative. So since we're only working with quotients of polynomials, we really only have to check that this works on a power function. In other words, a monomial like x squared or x cubed or so on and so forth. And then after that, everything will follow from a product rule and a quotient rule and so on and so forth, which all of those will hold in this calculus, as I'll let you guys check if you want to. So let's just go ahead and work out the only example that we really need to work out, and that would be the example if f of x equals x to the m, and here I'll just say that m is some natural number. Maybe some natural number including 0. And then from there you can extend it to all integers or something if you want to. Okay, so let's go ahead and see if this derivative works and gives us the same kind of thing as it would for the real variable calculus derivative. So here we'll have the derivative of f is equal to this limit as n approaches infinity of n times. Now we're going to plug x plus 1 over n into this power function x to the n. So let's do that, x plus 1 over n to the m power. And then we're going to subtract f of x, but that's just x to the m. Great. And now we're going to use a binomial expansion formula. So I just want to recall that really quick. So I'll recall it over here. So let's say we have a plus b to the m power. That's going to be the sum as k goes from 0 to m of m choose k, and then a to the m, a to the k, and then b to the m minus k. So we want to apply that binomial expansion formula to this guy right here. So let's see what we get. That's going to give us this limit as n approaches infinity, and n times, I'll just write out the first couple of terms because it's kind of obvious what will happen. So we'll have x to the m, and then next we'll have plus m over n times x to the m minus 1. So that would be like m choose 1, and then we have 1 over n to the first power. That would be like playing the role of our a to the k over there. And then next we would have m choose 2, and then 1 over n squared x to the m minus 2 plus ... Great. And then finally we subtract x to the m from this. Okay, great. And now what I really want to notice here is that this x to the m term is going to cancel with this x to the m term. And all we're left with is this m over n x to the m minus 1. And then everything out here can be written as 1 over n squared times a bunch of other stuff, because the exponent of 1 over n squared in the binomial coefficient is increasing as we move out that way until we get to this very, very last term, which is, by the way, 1 over n to the m power. Okay, great. So when all is said and done, we have this limit as n goes to infinity. Notice this n is going to multiply onto this term and give us m x to the m minus 1. Then this n is going to multiply onto this term and give us 1 over n times a bunch of other stuff. But now as n goes to infinity, this guy is going to go to 0, and we're left with m times x to the m minus 1. So it looks like it makes sense to define our derivative on this power function, and then we can boost that to a definition of a rational derivative on rational valued functions. In other words, functions that are ratios of polynomials when you're just considering the domain as the rational numbers. Okay, so now that we've kind of seen that the derivative works, I want to look at some classic theorems from Calculus 1 to see if they still hold. So it looks like we were able to define a derivative, or at least a hack of a derivative, on our calculus for the rational numbers if we only considered rational functions, that is, ratios of polynomials. Now I want to look at 3 classic theorems from Calculus 1 and see if they're still good to go. So let's first look at the intermediate value theorem. So let's recall that if f is continuous on the closed interval a to b, and y is some number between f of a and f of b, so we don't know the order of f of a and f of b, so it's just between them, then there exists a c in the open interval a, b, such that f of c equals y. Okay, great. And we're actually going to show that this does not hold on the rational numbers, and we're going to do that by the following example. So let's consider this function. Let's consider the function f of x, which is equal to x squared minus 2. So notice that's a nice continuous function on the real numbers, and thus it's continuous on the rational numbers as well. Another thing that I want to notice is the following, that f of 0 equals, well, 0 squared minus 2, which is equal to minus 2. And f of, well, let's maybe use 2. So that's equal to 2 squared minus 2, which is equal to 2. Great. And so here's what we have, just to spell it out really carefully. F is continuous on, and I'll write it like this, the interval 0 to 2, but I'm intersecting that with the rational numbers. And the number 0 is between f of 0 and f of 2, right? Well, I mean, that's pretty obvious because negative 2 is less than 0, which is less than 2, and 2 is equal to f of 2, and negative 2 is equal to f of 0. Great. But there does not exist a c such that f of c equals 0. Great. And we can actually see that because by way of contradiction, let's suppose such a c exists. Well, then we would have f of c equals 0, but that would be the same thing as c squared equals 2 by our equation up there. But since we're only working over the rational numbers, that would tell us that c was in the rational numbers, which is not true. So what's going on here is this kind of typical example where we have a hole. So we're exploiting the fact that the rational numbers are full of holes. So we've got this parabola. So it obviously goes through like root 2 and negative root 2. So it has that kind of picture right there. Great. But this isn't a solid curve. Notice it's got a hole right here at the point 0 because that point doesn't correspond to a rational number. Okay, so it looks like the intermediate value theorem is not good to go, even with the standard polynomial example. So let's maybe like revisit this with the mean value theorem. So we just showed that the intermediate value theorem failed on our calculus of the rational numbers. Now let's check the mean value theorem. So let's recall what it says over the real numbers. So we want to suppose that f is continuous on a closed interval a, b, and differentiable on the corresponding open interval. Then there exists a c, which is on that open interval, such that f prime of c equals f of b minus f of a over b minus a. In other words, the slope of the secant line equals the slope of the tangent line. Okay, so we're going to exploit this hole in the rational numbers at the square root of 2 again to find a counterexample for the mean value theorem on our calculus. So, and the function that we're going to look at in this case is given by 1 over x squared minus 2. Great. So this thing is actually continuous at all rational numbers. So continuous on all of q. Great. So that's actually easy to check because from calculus 1, we know the only place that this is not continuous is root 2 and negative root 2. And furthermore, it's differentiable on all of q as well. And you can check that the only places that it's not differentiable on r are the square root of 2 and negative the square root of 2. So this definitely satisfies this setup that it is everywhere continuous and everywhere differentiable. So now we can restrict to a certain closed interval and corresponding open interval and see what happens. So let's maybe consider, and obviously we want our closed interval and our open interval to sandwich one of these bad points. So let's maybe consider the closed interval 0 to 2, and I'm going to go ahead and intersect that with the rational numbers just so that we only have rational numbers in there. Good. And now what I want to notice is that if we take f of 0, we'll get 1 over negative 2, so that's equal to negative half. And then if we take f of 2, we'll get 1 over 2, so that'll be a half. Now we can go ahead and find that slope of the secant line, in other words, the average change. So f of 2 minus f of 0 over 2 minus 0. So let's see, that'll be a half minus negative a half, which is 1 over 2, so that's equal to 1/2. So we've got our average change of a half. Now we're going to try to find a place where the instant change equals a half as well. So in order to take this derivative, I'm going to think about it as x squared minus 2 to the negative 1, so I can employ the chain rule. And so that's going to give me a derivative of minus 2x over x squared minus 2 quantity squared. Now I want to notice that all x values on the open interval corresponding to this closed interval will give us a negative slope here. And that's because if we plug in a positive number to the numerator, we get a negative number from this minus sign, and then the denominator is always positive because we have this thing as squared. So that's like negative divided by positive, which is going to be negative. And let's just reiterate, this is for all x on this corresponding open interval 0 to intersect q. Great. But what that means is that it can never equal a half because a half is obviously not negative. So in other words, the mean value theorem won't work in this rational calculus setup either. Okay, and maybe I want to look at a little picture of what's going on here. So let's maybe think about the graph of this thing. So thinking about it from calculus, we know that we've got these asymptotes at plus minus square root of 2. And furthermore, we can sketch in the rest of it in the following way. So it's going to look something like this. Good. And now what I want to point out is to the right of the y-axis, this function is always decreasing. In other words, it has a negative slope everywhere, but the secant line that we just calculated is something like that, which clearly has a positive slope. So obviously there's that asymptote at the middle, but because that asymptote occurs at an irrational number, our function is actually continuous on its whole domain, which is considered to be the rational numbers. Okay, so I'm going to go ahead and clean up the board, and then we're going to look at an example of the extreme value theorem. So we just showed that the mean value theorem really required the real numbers. It would not work on our calculus of the rational numbers. Now we're going to repeat that process for the extreme value theorem. So let's recall what that says. We want to suppose that f is continuous on a closed interval a, b, then it achieves its maximum and minimum on this set. Now, we're going to do this the same kind of way that we did before. In other words, build a very simple example out of the fact that the square root of 2 is not rational. So let's maybe consider this function. So it's going to be x squared minus 2 quantity squared. So now notice this thing is continuous everywhere and differentiable everywhere on the real numbers, and thus it is also on the rational numbers. So what I want to do is use the fact from calculus 1 that we know that these extreme values have to happen at critical points in order to kind of hack together what is missing here. So we'll take the derivative of this thing. Again, we'll have to use the chain rule, so that's going to give us 4x times x squared minus 2. So that means we've got critical points at x equals 0 and x equals plus minus the square root of 2. But since we're outside of the rational numbers, we really only have these critical points at 0. Good. Now the next thing that I want to do is notice that we could graph this thing. And if you graph this thing, it has the following picture. So it's going to look like this. So it's going to look like that, but the problem here is that these minimums occur at plus minus the square root of 2, which means they're wholes. So all we have to do is consider some sort of rational interval around one of these holes, and we'll see that we have a problem. So let's maybe consider this rational interval from 1 to 2. In other words, let's consider this interval 1 to 2 intersect rationals. And what we want to claim is that this function does not achieve its minimum on this interval. And I want to point out that this interval is something like from here to here. Good. So let's maybe make that claim. So claim f does not achieve its minimum here. Great. And let's maybe do that. So let's see how this proof goes. So the first thing that we want to notice is that f of x is bigger than 0, strictly bigger than 0, for x in the interval 1, 2, if we intersect that with the rational numbers. And that's clear because the 0 that it has is at the square root of 2, but that's outside that rationalized interval. So the next thing that we'll do is work via a contradiction. So in other words, we're working by way of contradiction. We'll suppose that we actually do achieve a minimum. And so let's, by way of contradiction, suppose that f of x naught equals m, and that is the minimum on this interval. Great. And then this is going to boil down into two cases, and here's where this turns from like something a little bit more careful to something a little hand wavy. And this first case is if x naught is less than the square root of 2. So in other words, x naught is here. Great. Then what we need to do is find some n, which is a natural number, such that x naught plus n lives in between x naught and the square root of 2. So let's maybe see how we could do that. We could have x naught, which is strictly less than x naught plus 1 over n, which is strictly less than the square root of 2. Good. So we can always find a 1 over n, which is less than the square root of 2 minus x naught by the Archimedean principle. Okay, good. So, but now what we want to notice is that by the behavior of the function, if we evaluate the function at x naught plus 1 over n, we'll get a number which is smaller than x naught. So let's write that down. So f of x naught plus 1 by n is smaller than f of x naught, but that's equal to the minimum. So we found a value of the function which is smaller than its minimum, which is a contradiction. And then the other case is essentially the same, just reflected across this point right here. Okay, so it looks like the extreme value theorem is not good either over our rationalized calculus. Now I'll clean up the board and really point towards what is going on here. Okay, so now we've seen that a lot of things go wrong when we work in calculus over the rational numbers. In other words, this rationalized calculus. And at the heart of it is this axiom of completeness of the real numbers. So that says the following. So every non-empty subset of the real numbers which is bounded above has a least upper bound. So we're not going to get into the technicalities of that, but I have a real analysis playlist that's kind of being built right now that has some of this stuff in there. And what happens is that this axiom of completeness is one of the important seeds in the proof of the intermediate value theorem and the mean value theorem and the extreme value theorem. And furthermore, if you assume any of these theorems, in other words, if you assume the intermediate value theorem is true, the mean value theorem is true, or the extreme value is true, extreme value theorem is true without assuming the axiom of completeness, these will also imply the axiom of completeness. So in fact, these are kind of like equivalent formulations. Okay, so I think that's a good place to stop.